Today, we are going to discuss one of the most important concepts in machine learning called the machine learning lifecycle. The machine learning lifecycle describes the complete process of building, deploying, and maintaining a machine learning model in real world applications. Machine learning is not just about selecting an algorithm and training a model. Instead, it is a systematic process that starts from understanding the problem and ends with continuously monitoring the deployed model. In this, we will go through each stage of the life cycle in a clear and structured way so that we can understand how machine learning projects are actually implemented in industry. So in this slide, if you can see the stages of machine learning life cycle, each stage depends on the previous one, and mistakes in early stages can severely affect the final model performance. The life cycle ensures proper problem understanding, high quality data usage, correct model selection, reliable deployment, continuous improvement after deployment. By following this life cycle, we can build machine learning systems that are accurate, scalable, and sustainable. So the machine learning life cycle starts with the broad problem identification, followed by the data collection from various sources, followed by data cleaning and pre-processing of data, followed by data exploration analysis with the help of various statistical tools, followed by feature engineering and selection, feature creation, and feature transformation. So model selection. So next one, model training, model evaluation, and finally model deployment, model monitoring, and model maintenance. So there are various phases. Each phase plays a prominent role. The next screen. So every machine learning problem starts with a broad problem identification. So here if we can see, the first and most crucial stage in machine learning lifecycle is problem definition. In this stage, we clearly define what problem we are trying to solve, what input data is available, what output we are trying to expect, what constraints exist, such as time constraints, cost constraints, or accuracy constraints, how success will be measured. We also decide the type of machine learning problem, such as classification, regression, and clustering type. As well, defined problem ensures that data collection and modeling build aligned with the final objective. For example, the loan approval can be defined as a binary classification problem. Sales forecasting can be defined as a regression nature problem. Customer churn prediction is also a classification problem. If the problem is not defined correctly, even the best algorithm also will be failure. So the next one, the data collection. Once the problem is defined, the next step is data collection. Data is collected from various sources, as we have discussed earlier: structured data sources, unstructured data sources, semi-structured data sources, and metadata sources. Once the problem is defined, the next step is called data collection. Data is collected from various sources such as databases, sensors, and logs, and APIs, application programming interfaces, and online platforms. The goal is to collect sufficient, relevant, and representative data that truly reflects the real world scenario. Depending on the application, data can be historical data, real time data. Good data collection practices are essential because poor data leads to biased models, insufficient data reduces accuracy, unrepresentative data causes unreliable predictions. So, therefore, there are few examples: collecting transaction records from a bank, gathering website clickstream data, collecting sensor data from IoT devices. Remember, model quality depends heavily on data quality. So the next one, data cleaning and data pre-processing, which plays a prominent role. Raw data collected from real world sources is usually incomplete, noisy, and inconsistent. Therefore, we perform data cleaning and pre processing tasks. These stages include handling missing values, removing duplicate records, fixing inconsistent formats, encoding categorical variables, normalizing or scaling numerical features, detecting outliers, removing outliers. Outliers may be treated or removed based on domain knowledge. Examples: filling missing age values using mean or median, encoding gender like 1 is equal to male, 2 is equal to female, or locations like 1 is equal to urban, 2 is equal to semi-urban, 3 is equal to rural, standardizing data formats. This step is extremely important because clean data leads to better learning and more accurate models. The next one is exploratory data analysis. After cleaning the data, we perform exploratory data analysis, commonly called EDA. EDA helps us understand data distributions, identify patterns and trends in the data, detect outliers and anomalies of the data, find corrections between the variables. So that's the reason why we will try to apply descriptive statistics and inferential statistics. We use statistical summaries, visualization such as graphs and plots, various types of graphs and plots like bar chart, pie chart, line chart, vertical bar chart, horizontal bar chart, scatter plots, heat map, and we will use various types of charts to understand the data distribution. EDA guides, feature engineering, model selection, data quality validation, and example, plotting salary versus experience. As higher the experience, higher the salary may be. So to generalize such kind of conclusions from the data, using correlation heat maps, checking distribution of customer purchases. So EDA, exploratory data analysis, gives us deep insights into the data before modeling begins. So the next one is feature engineering and selection. In this stage, we focus on creating a new feature, selecting a new feature, feature transformation are the most meaningful features. Feature engineering involves creating new features from the existing data, transforming raw data into informative representations. Feature selection involves removing irrelevant or redundant features, reducing dimensionality of the data, preventing overfitting. Good features often have more important than complex algorithms. For example, creating a total uh, expenditure feature, creating a BMI, body mass index, from age of the person, height of the person, and weight of the person. These three features, by using these three features, we can create one new feature. We call it as BMI, body mass index. Selecting top features using RFE or mutual information, extracting day or month from timestamps. Effective feature engineering significantly improves model performance. The next one, model selection. Now we select the most suitable machine learning algorithm over here. The choice depends on the problem type, the type of the problem, data size, feature complexity, interpretability requirements, deployment constraints. We often compare multiple models before finalizing one particular model selection. Example, logistic regression versus random forest algorithm, conventional neural network for image classification, support vector machine for text classification. So there are various algorithms are specifically designed for various problems. So we have to select a right algorithm for a right problem. The goal must be in such a manner, the selected model must have accuracy, must be complexity, interpretability. Choosing the right model is a strategic decision in entire stages of machine learning. So next one is model training. In the model training stage, the selected algorithm learns patterns from the training data. Training involves feeding inputs to output pairs, minimizing a loss function, adjusting model parameters. Uh, Key considerations over here, learning rate assessment, batch size assessment, number of epochs, and regularization aspects. There are various aspects which fall under this model training. Training a decision tree classifier, fitting a regression model, training a neural network using back propagation. Proper training ensures the model learns generalizable patterns, not noise. The next one is model evaluation and fine tuning. After training, we evaluate the model using validation or test data. Evaluation metrics depends on the task, majorly accuracy of the model value, precision values of the model, recall values of the model, root mean square error values of the model, F1 score of the model, and there are various parameters which facilitates for to evaluate the effectiveness of the model. We also perform hyperparameter tuning using grid search approach, random search approach. Techniques like cross validation help to avoid overfitting and underfitting of the model. Confusion matrix, ROC curve, performance matrix analysis. The objective is to select a model that generalizes well to unseen data, which is a new data. The next one is the model deployment. Once the model performs well, it is deployed into a production. Deployment method includes various application programming interfaces, web or mobile applications we will try to use over there to for model deployment, and we will take the help of various cloud platforms, edge devices, and important considerations, scalability of the model, latency of the aspects, security aspects. For example, fraud detection, API in banking, recommendation systems in e-commerce, sentiment analysis in cloud services. Deployment allows the model to create real-world value. And the last one, final one is model monitoring and maintenance. Once after the model deployment, the model is continuously monitored for performance and data drift. Monitoring ensures that the model remain accurate as real-world data and conditions change. The final stage is model monitoring and maintenance. After deployment, model performance can degrade due to data drift, changes, changing user behaviors, new patterns. Due to this, the model performance might be decreased. So monitoring ensures accuracy remains the stable, prediction remains the reliable. Predict, retraining and updates may be required. Example, monitoring demand forecasting accuracy, updating spam filters, detecting data drift. This stage completes the life cycle and ensures long term sustainability.